calculus lesson on 7.5, general integration. This is part of your note that you should memorize. Okay, there are a whole bunch of stuff that we've done in the past that you should know. And there are a few stuff that we haven't done. I believe I shared something similar to this before. And okay, we're not doing this, and we're not doing this. And you should commit these to your memory right here, 11 through 14. And some of these we've done already in a trig substitution. Okay. All right. Why don't we just do one of them? How about number 11? All right. So this is one of those things that is not very intuitive. We right off the top of our heads, we don't know what's going to happen, right? I just don't see, right? What could create when you take the derivative gives you secant x. So after many trials, somebody has discovered this. So this is what they've done, okay? So given this, you say secant of x times secant x plus 10x, secant x plus 10x, top and the bottom, like this. And decide to take u as secant x plus 10x, like this. Now, when you take du, what do you suppose will happen, right? Well, the derivative of secant is secant x 10x, and the derivative of the 10x is a secant squared x, and then we're gonna have dx on this side, right? What do you notice when you distribute this right here? I get the same exact expression, don't I? All right, to make it more obvious, let's factor out the secant x. Then we're left with secant x plus 10 of x. I know I swapped the order. So what we end up with this expression right here is equal to this, right? That's du. So it becomes 1 over u du, right? Well, if that's the case, the answer is ln of absolute value of u plus c. But what is u? That's ln of secant x plus 10 of x plus c. Now, this is one of those things where it's not very intuitive, but after many trials and errors, somebody figured out a way to do this. And you could do something similar with this, but I normally don't say this, but I would just simply commit this to memory, right? Usually in favor of you guys deriving things and whatnot, but because this isn't all that intuitive, I would just memorize it, okay? But you should still try to derive it a few times as well, okay? All right, let's take a look at this. The next page, and it lists some of the procedures that you should sort of think about, right? So if you have, let's say, an integration, something like this, it might be easier if you just expand it out and integrate individually, okay? How about this over here? You do the same thing. Oops, that kind of looks like what? Inverse trig function, right? And this one, you could take that as u, and you could do u substitution, and so on and so forth. And I think we've done this before, right? Where I believe that's a square, if I'm not mistaken. Okay, let me just double check. Yeah, it is. It is. That's a square. My bad. That's a typo. Okay. And so when you have something that is in a quadratic, you might want to have a 1 minus a square of a variable squared, right? And then here are a few others. You should be copying this sum, obviously, right? And when you do a long division, you get this, and this looks like a inverse trig to me. When you have this expression in here as well, you could be a little bit more imaginative and add 2 and subtract 2. And then what you end up with is we got quadratic over here, and you could do a long division and whatnot. And you could use a whole bunch of trig identity. I just wrote down one of them, but there are 2 others that you should know, right? And then we got something like this. You could multiply with a conjugate, and you could use the Pythagoras relationship to get something like this, Okay, so there are all these little tricks. So you should take a look at this and sort of keep this in the back of your mind as we practice. Okay, you can use this as a guide. Okay, let's look at 3 questions that look very, very similar, but they're ultimately different. Okay, now look at this. That x squared plus 1 looks very familiar, right? Right, so all you have to do is first factor out the 4, and we'll end up with x squared plus 1 over x squared plus 1 dx. And we know that integration portion is what? Inverse tangent of x plus c. Now, this one, while it looks very, very similar, right? It's not. It really isn't. So here, what we could do is take the denominator, x squared plus 1, as a du, right? And that comes out as 2x dx. So, oopsie, I don't know why that's doing that. So that when you have this integration over here, I could just rewrite that as 2 times 2x dx like this over x squared plus 1. So this portion is du. The 2 in front of that comes out in front of the integration. So that is du, and the denominator is just u, isn't it? Right. It's probably better to write it this way, right? And that is ln of absolute value of u plus c. And then that right there is ln of x squared plus 1. You actually don't need absolute value here because when you square something, its minimum value is not negative. It's a 0, right? Plus 1. So this expression is always positive. So you really don't need absolute value here, right? On top of that, we could actually pull this up here, right? Using the log property. So you could actually express that as ln of x squared plus 1 squared plus c. Even though they look very similar, ultimately where you approach them is very, very different. Now, we're going to increase the numerator by another degree, right? And what do we do in this case? In this particular case, what we're going to do is, what color did I use? All right, let me go back to using black. Okay, let's do a long division, shall we? So when you do that, x squared plus 1 goes in 4 times. 4x squared plus 4, subtract minus 4. So this expression is 4 plus 4 over x squared plus 1 dx. Hold on a second. Isn't this basically integration of 4 dx? Let's separate them. Okay, didn't we do this already? Yes, we did. So that portion is inverse tangent of x plus c, and that's simply 4x, right? So we got 3 integrals that look very, very similar, and yet the outcome can be very, very different. The approach can be very different. So in this particular case, when we did the long division, the part of it, this part, look exactly like this, right? But here, though, we do straight up u substitution. So whenever you have something like this, if the degree difference is only 1, there's a good chance that you're going to do u substitution. And if you have something like this, some quadratic format or square root of quadratic format, you may be doing, the result may be either the inverse tangent, inverse trig, or if it's square root of that, it's an inverse, trig substitution, okay? So just keep that in mind as we go along. The next page is your turn. So do me a favor. We're going to do this in class, but why don't you do at least, I don't know, how about 2? I want you to try this one and this one, and I'll be checking for it on your note submission, okay? All right, guys. We're now going to move on to the second phase of the notes, which is 7.7 trapezoidal rule. You could follow this link right here, guys, that you see before you. And if you do, you're going to get this. And I gave you a link to where I got the picture from. Let me go back to where it was. There you go. So using this particular example from 5.1, and we estimated the area back then, y equal to 16 minus x squared from 0 to 4 using 4 rectangles, right? We're going to left endpoint Riemann sum, the sum of the areas. We got right estimation, right? And then we have the middle, using the middle point. So for example, in this one, you got 4 boxes, but we're going to use the left interval to determine the height like this. See that? So between 1 and a 2, right here, we're going to use the 1 to determine the height for that one, and so on and so forth. And this one, of course, we do the right-hand side. But because it's a decreasing function, that the right estimation will be underestimating. Here we'll be overestimating. And when we use the midpoint, it looks like we do under and over at the same time. And it appears that it should give you the best answer, right? At least out of the 3 anyways, right? So it's 43, right? But we're going to have another method, as the name suggests, is trapezoidal, right? So what do I do? I'm going to draw a box, right? Line like this. And I'm going to draw a trapezoid. And that's 1, 2, 3, 4 of them. But what is the trapezoid? Well, trapezoid looks like this. Let's call that change in x. That's B1, B2. Normally we call that height, right? Let's put it as height for now, okay? You know where I'm going with this, right? The area for this one, area of the trapezoid, is 1/2 of the B1 plus B2 times the height, or simply height over 2 times this. Me personally, I prefer to write B1 plus B2 divided by 2, and I think of that as average height between the two, right? And that makes a little more sense to me. But anyways, we're going to write it this way because in terms of calculations, it'll work out better. Why don't you go ahead and try to figure that out, right? Add up all the areas and see what general kind of conclusion you could come to. Okay, please pause the video. Okay, guys, so here it is, what you should have come up with. Here it is. So the entire area of the trapezoid is a sum of this for all 4 of them. So for the first one, it's 1/2. The B1, B2, the bases are actually 2 heights, the y values, right? So y value for this is 16, that's 15, that's actually 12, and that's actually 7. If you go ahead and do the calculations. So this one over here is what? 1/2 16 plus 15 times the width. So that change in x is 1. It's kind of convenient, isn't it? And for this one is 15 and 12. For this one is 12 and 7. And for this one is 7 and 0. So they all contain half and h, but h is 1. So factor out the half. What you'll notice is that there are 2 15s, there are 2 12s, and 2 7s. But the lone 2 values at the front and the end, these 2, there's only 1 of them, right? So I probably should have written down 1 times that, and then, hold on, let me create a little more space over here. 1 times that. All these values in the middle gets counted twice. So you do the calculation, that's half of 16 is 8. That's half of 2 times 15 is just 15, then it's 12 and 7, that's a 0. Add them up, you get 42, right? So the general way that we do this is, oh, by the way, this is assuming, right? This is a big assumption. Assume that is the change in x is constant, that it is same for all of them. Then you could sort of generalize this, right? You don't have to, it doesn't have to be constant. And then your calculations will be a little bit more involved, obviously. But the key idea here is that the ones in the middle here, heights, that they get used twice. So you double them. The ones in the end, it gets used once. So you only have 1 of them. That was it. Now, there was a question of you guys. What did you notice about the trapezoidal rule with L RAM and R RAM and midpoint RAM? We're estimating the left rectangle, the right rectangle, and the middle rectangle, right? So when we do this, right? If you said the area of the trapezoid with the n number of pieces is equal to the average of the left and the right, you're absolutely right. And we could even prove it actually. But I think for us, it's sufficient that we simply say, okay, this and this, what is that equal to, right? So 1/2 of L plus Rmn is what? 50 plus 34 is 42. Check. Okay. And I'll leave, if you'd like to do a derivation on this one, I'll leave that as an exercise for you guys. Okay. All right, guys. The next page is, let's do this. Okay, you could use the link over here and type that in and try to get the answer. I don't think this link has a trapezoidal rule, but I'm sure you could Google one if you need to. Why don't you take some time and try to figure that out? Okay, guys. And I did this using the midpoint rule, and you already know that the answer should be the average of these two, right? But be careful though, because these two are estimates, right? So your answer should be very close to the average of these two values. Okay. And second hint, right? And we want you to find the experiment was performed in which oxygen was produced at a continuous rate, and then there are time intervals. Okay. But the key difference here is that the time intervals over here, the change in x, change in time, that's 1, the difference is 2, and a 3. It's not an even interval, but it's okay. We can still estimate them. All right. So yeah, why don't you pause the video and go ahead and try to do this on your own first, okay? All right, welcome back. So here are the results. For this one, I went ahead and just drew the picture for, if you're going to divide into two pieces, right, between 1 and 2, there should be another point in the middle. That's 3/2. I just plugged those values into this function right there, and these are the values that I got. And applying the formula that I have, the gap, the change in x over here is half, right? Over 2 times the endpoints, some of the endpoints, height, the height of the endpoints, and then double the any middle heights. And when you go through the calculation, it comes out to 77 over 144, which is about 0.53472. And the only reason I did the decimal value is that we already have this value, right? I copy pasted from the link. Yeah, the left rectangle estimate was 0.722, and then right estimate was 0.347. So when I take the average, it was 0.5345, and that's very, very close to what I had. Yeah. All right, guys. So that's it. Okay. All right. How'd you do in the next one? Yep. This is the work that I had. Yeah. So this is individual height trapezoids like this, right? So I just used the formula between these two. So with this one, so 1/2, change in x over 2, right? Times the average of the two, the two heights. So I view this as like average of the two heights times the width. And the average of the two heights, which is this, times the width is 2, right here. Average of the two heights, which is this one right there, times the width, right there. I mean, I personally prefer to think of it that way. And when you go through the calculation, it comes out to 232.9 cubic feet. All right, guys. Yeah, that is it. So if you have any questions or concerns or worries, we could talk about it in class, right? All right. So let me just go through a quick sort of like overview of what's going on. So in a trapezoidal rule, the big takeaway is that we're using trapezoidal formula to calculate the area. And if you look, we will either slightly overestimate or underestimate, but it's a lot better than left and the right, isn't it? And calculation is about as easy as left and the right estimation. But the midpoint can get a little annoying, right? So I think this is a good alternative, right? If you had to estimate it by hand, okay? And then the big takeaway that I had over here is this, right? The trapezoidal estimation, right, was same thing as left rectangle approximation method, right? So we added a bunch of rectangles from the left interval, on the left interval, and we add a bunch of rectangles on the right side of the interval. And this one stands for midpoint rectangular approximation method. And as it turns out, the average of these two was equal to the trapezoidal approximation. All right, guys, that's it. So we'll talk about the rest in class. Okay, I'll see you then. Good night.